Hello, biology superstars. Welcome to the HL content for A 1.1, all about water. Remember that in theme A, we are in the theme of unity and diversity, and in level of organization 1, we are looking at the molecular level, and hopefully you're coming from the SL video and have a little bit of information about why we're looking at water in this particular cross-section. The HL content is pretty short, only 2 points of information, so let's get started. All right. Our associated skill in this part of the content is reading a graph with a logarithmic scale. And I think it'll become obvious why we're doing that when we look at the graph, and then we'll go over the notes. So we look at logarithmic scale graphs here because you often show the deuterium to hydrogen ratio in ancient water supplies, or really like in the water supply that's on the planet, using a logarithmic scale. So this graph that we're looking at shows on the y-axis the deuterium, and I get my pen going, the deuterium to hydrogen ratio of water molecules that are present in a variety of different places in the universe. So like here's Earth, obviously. Here's the Oort cloud. Here's the Jupiter family. Some people will recognize Halley's Comet. And then like a bunch of different asteroids. We'll get into why this is important once we get into the points of information. And then like spread out through here are some of the other planet names that you might recognize from our solar system. So when we're looking at the deuterium to hydrogen ratio of water molecules, we are looking at these spread out over a very wide scale. So that's why we're looking at these on a log scale. When you use a logarithmic scale, I'm going to see if I can start writing. When you use a logarithmic scale, you are multiplying. So on this y-axis, these numbers are changing exponentially. This is in contrast to a linear scale where you're adding as you go up your axis. So a log scale allows you to show a much bigger range of numbers. We're looking at this second question here. Allows a larger range of numbers. So these ratios are super different, and they can all be expressed in the same scale. And the scale used is the log scale. And other than that, there's not so much. I don't think you need to like know deep information about how to look at a log scale. When you look at this particular log scale, you will notice that Earth and these asteroids all have similar deuterium to hydrogen ratios. We'll talk about that in the points of information. So I think let's get started with the notes. I think that's all I have to say about that. All right, clearing and moving forward. So in our very first point of information, we'll start talking about those asteroid versus Earth deuterium to hydrogen ratio numbers. A 1.1.7 is about extraplanetary origin of water on Earth and the reasons for its retention. The abundance of water over billions of years of Earth's history has allowed life to evolve. Limit hypotheses for the origin of water on Earth to asteroids. So there's those asteroids that we were just looking at that had the same DH ratio. And reasons for retention to gravity and temperatures low enough to condense water and trap it in the atmosphere of our planet in what we call the water cycle. So extraplanetary origin of water on Earth. This BYA means billions of years ago, so the formation of the Earth is estimated at around 4.6 billion years ago. The theories about the origin of water are primarily related to heavy asteroid bombardment. So those same asteroids that we saw with that same DH ratio were probably hitting the planet and leaving water on the surface of the planet. This is like a little asteroid rock filled with crystallized water, like ice crystals, and outer space is full of these. And the ones that came and broke into the atmosphere of the Earth when the planet was forming, like, sure, that's the Earth. Here's the atmosphere. And these asteroids that came and hit the surface of the Earth, like really all the way back when it was a protoplanet, probably, stayed in our atmosphere because of the heaviness of the gas and the placement of our planet in the solar system, and all of that water stayed on the surface of the Earth. And that's been essential for supporting life. So I think that's all I have to say about that. Reasons for its retention, we already talked about a little bit, is the appropriate temperature of this planet due to the distance of Earth from the sun. We'll get into this again in the next point of information. And the idea of gravity. Earth has a strong gravity, and it pulled those water molecules down towards its surface as the planet was forming. All right. So the next thing is the relationship between the search for extraterrestrial life and the presence of water. And here we'll talk about the idea of a Goldilocks zone. So my picture here is Goldilocks and the Three Bears. And you might remember this story where, like, there was always some, like, Goldilocks was broken to the house of these poor bears and kept, like, messing up all their stuff, and would always find first a set of stuff that was, for example, like porridge that was too hot, and then too cold, and then just right. And that happened with everything. Like the beds were too hard and too soft and just right, and the chairs were too big and too little and just right. And she, like, broke all their stuff trying to make herself comfortable. And this is actually, so this fairy tale was, like, based on a literary rule called the Rule of Three, where something is, like, wrong in one way, and then it goes wrong in the opposite way, and then it works out. And that rule was sort of adapted by astrophysicists to talk about Earth and why Earth has, like, worked as a planet that supports life. So let's go forward here. In order to be habitable, a planet needs water. And the Goldilocks zone, as it relates to astrophysics, means that the temperature of the planet cannot be too hot or too cold, and those twos have the wrong number of O's, but we're just going to ignore it. It has to be just right. And in our solar system, Earth is the planet that is just right. So when we look for extraterrestrial life, we are looking for other planets and other solar systems that are at the same distance from their center of the center of their solar system. They're, like, whatever you call that. They're the star that everything is rotating around in their solar system, their sun. And it is estimated that there are 40 billion planets like that in our galaxy. So when we look for, I don't know, are we looking for extraterrestrial life? Who knows? But if we were to look seriously for extraterrestrial life, these are the planets that we would want to look at. All right, and I think that's it. That's all we have to talk about for the HL content for A 1.1. So I hope that this was helpful.